Well, good afternoon, and welcome everyone to today's Southern Fire Exchange webinar. My name is David Godwin, and I'm the coordinator for the Southern Fire Exchange with the University of Florida. This webinar is a special collaborative program that was developed in partnership with the Southern Fire Exchange, the Desert Research Institute, the National Weather Service, the NWCG Smoke Committee, NC State University, and the North Carolina Montgomery Community College. Today we're excited to have our guest speakers, Matthew Fearon, researcher with the Desert Research Institute, and Robyn Heffernan, fire weather science dissemination meteorologist with the National Weather Service. Today Matt will be giving a presentation that will review and explain the strengths and weaknesses of several methods for determining atmospheric mixing height. And afterwards, Robyn will give a report on National Weather Service mixing height programs. So, without any more hesitation, let's introduce our speakers today. Matthew Fearon has been employed as a research scientist at the Desert Research Institute in Reno, Nevada since 2010. Prior to 2010, Matt worked in the private sector and in academia on various research projects, integrating meteorological concepts into product development and participating on collaborative peer-reviewed research projects. His research interests include the study of mid-latitude and tropical weather systems at both synoptic and mesoscales, with particular interest in tropical-extratropical interaction, precursor storm environments, flows associated with complex terrain, and boundary layer dynamics. Matt completed his bachelor's in meteorology from the University of Massachusetts Lowell in 1998, a master's in atmospheric science from the University of Nevada, Reno in 2000, and he is almost completed with his doctoral degree in atmospheric science from UNR. Robyn Heffernan is the National Weather Service Fire Weather Science and Dissemination Meteorologist, located at the National Interagency Fire Center in Boise. Since 2011, Ms. Heffernan has been responsible for leading several technological and science-based efforts for the National Weather Service Fire Weather Program, as well as integrating these efforts into fire weather operations. She's the current chair of the NWCG Fire Environment Committee. So welcome, appreciate your efforts, Matt and Robyn, joining us today, and we're excited to have you, and thank you everyone who's joined the webinar session. So let me move right ahead for Matt's presentation. Here you go, Matt.
All right, thank you, David. Appreciate that introduction. Appreciate the opportunity to talk to you guys today, and I'm glad that there's such a big turnout. It's great news. This project has kind of been ongoing for a little while now. My co-researchers, Tim Brown and Gary Curcio, helped me out a lot on this project. It was basically looking at 4 mixing height methods and determining which one would be the best way to get at operational prediction in an operational environment. And there's plenty of other techniques that I didn't review, but these were the kind of the top that would be good for operational reasons. And so I'll just kind of get into it. I've given this presentation a few times in a lot of in other places, and so I kind of condensed it down for this webinar. And you know, I wanted to leave time for questions at the end because I bet there's probably a lot, and I just encourage that at the end. If there's something here I didn't talk about just so, or you didn't understand, or I left out, I really want to hear from you. I want to try to address all those questions. So I'll just start with kind of the motivation of what we're trying to do. Basically is to find, like I said, a good operational prediction method that is kind of better than what's in place now, and the next slide sort of speaks to that a little bit, but it mainly is the Holsworth method, which was developed kind of in the late 60s by George Holsworth, which is really not a bad method. It's very simple, and it's very quick, and it gives you a reasonable estimate. It just tends to underestimate what's going on in the atmosphere because it assumes a dry, static environment. But also what happens is with other methods that are being used by different folks, sometimes the mixing height is different. It's too high or too low, and that can be a problem if it's not consistent. And then there's just a few other reasons why it's important to keep mixing height consistent, which Gary Curcio has kind of been a big advocate for. Is, if you have county boundaries and using a method in one county and a different one in another, it changes the mixing heights, which can be hard for users. So it's important to keep the mixing height method consistent and basically maximize burning opportunities when they exist. So this next slide here shows a small survey that actually Gary put together for me for the paper. It basically shows 2 samples per region, weather forecast region. And you can see from just a quick scan of the methods used, you can see Holsworth is used most places. Again, this is just a small sample, but I think it carries some weight. A couple places weren't really sure what method they were using. They probably just had a procedure in place that they followed, and that's fine too. But this just kind of gives a quick overview of what's being used and where, and you can see most of the country is using the Holsworth method, which again is not a bad method. It's just it tends to underpredict because of its concentration on a dry atmosphere. So I'm going to talk about the 4 methods that I looked at in this study. These first 2 that are on this current slide are the Holsworth method, which is most widely used, and the Stoll method, which is also a pretty popular method and isn't much different than the Holsworth method. It's just it looks at the atmosphere in an unsaturated environment. In other words, you have moisture included, which is good. It helps mitigate inversions near the bottom of the atmosphere in certain cases when the inversion might be really, really small or really tiny. And it's just good to include moisture. I mean, why wouldn't you have it in there? I just think it's important, and sometimes it can make a really big difference, even if there's only a small amount. So the main difference between these 2 methods is one uses a variable called the virtual potential temperature, which looks at unsaturated atmosphere, and that's Stoll. And then the Holsworth, which uses the potential dry potential temperature, which is just a dry look at the atmosphere. And basically you take the surface parcel up from the surface and see where it intersects the environment for a particular sounding. And then where that intersection occurs is the mixing height. And it's pretty straightforward. And so those are the 2 kind of static stability methods that I looked at. And then there's 2 other ones in this next slide that look at both the static stability and the dynamic stability. And by dynamic, I mean just involving the wind and the shear associated with the wind. So there's 2 methods, the Bulk-Richardson number on the left, which kind of gives a nice description of what that is. But it's basically a ratio of the static stability over the wind shear. And that ratio, you can get a unitless value that can kind of give you an estimate of what, and how, basically a profile of what the atmosphere is doing. And based on some threshold values, you can determine the mixed layer height with those values, which I kind of get into in the next couple slides. So that's kind of how that Richardson number is defined. If there's any questions about that, I can answer that afterward. On the right-hand side is the turbulent kinetic energy, which is another dynamic and combined dynamic static measure of the mixed layer. And that takes into account just about everything you could think of. I mean, you got the wind, the advection of the wind, you have the buoyancy, production and consumption, the shear, transport, pressure perturbations, all combined into one kind of complicated equation. But it's also, it just gives a profile of values, and basically wherever the TKE, wherever it dissipates with height, you can find a threshold and categorize the top of the mixed layer with it. And I understand that it's a kind of a complicated measure, but if you're going to be estimating the mix layer from a numerical model, which I think most Weather Service groups are now doing with a model sounding or some kind of information from a model, it calculates that for you. And I think the North American model actually has a parameter in it now called PBL height, which is an estimate of the top of the mix layer using TKE. So those are some options that exist. I'm not exactly sure what a particular forecaster might do. What's their procedure? I mean, are they going to manually use a sounding, or are they going to use specific information from the model? These are just some things I came up with, and I hope they're useful in the decision making going forward. So these are just a couple examples of the Richardson number and TKE, and basically how I would pick off a particular mixing height. So on the left side is just a sounding of TKE with height. And so the threshold I chose is 0.1 joules per kilogram, which is a reference value, and I can get the citation out, and it's in the paper as well. But basically, that's where the TKE dissipates with height. And so in this case, the mix layer would be that horizontal line, about 2.8, say, kilometers. And then on the right is the same kind of information just from the Richardson number. And basically that value threshold was 0.505, which is another reference value that I found in the literature of where typically a mixed layer height would be given that number. And in this case, it's around 2 kilometers if you look at where that horizontal line intersects. So those are just kind of a flavor of the 4 methods and how they're used. And so now I'm going to kind of go through some results of those methods and how they sort of compare to each other. But before I do that, I just want to introduce this other basically LiDAR information that I use. So when I did this study, I took the 4 methods and I used model analysis, not forecast, but model analysis soundings, peppered all across the country. And then I compared basically the Calypso LiDAR from NASA, the value that I would get of mixing height from it to these methods, and try to determine which method was sort of giving me the best mixed layer height. And I used Calypso as my observed information, which has some good pluses and could have some minuses, but it just gave me more opportunity to look across the country rather than just using soundings, because I was just limited in basically 1 to 2 or 3 locations at most per state, whereas this way I could look at several grid points per state. But the Calypso LiDAR allows you to get at the mixing height using what's called the vertical feature mask, which is basically a representation of all the constituents in the atmosphere. And in this case, I used aerosol, which is the orange in this picture, and basically looked at the profile of aerosol. And I had some rules that attached to that, but basically if the aerosol was in contact with the ground, that was one of the main rules. And basically, what is the vertical extent of that aerosol? And that became my mixed layer height. So in this particular example, it would have been about 2.5 kilometers if you look at that right panel and look at the depth of the aerosol. And so I would compare those depths of aerosol to the 4 other methods that I got from model analysis output. And so here's a comparison of all those methods against the LiDAR values. And in this particular graphic, it shows box plots, and I think there's maybe over 2,000 different points compared. And this is all based on maximum mixing height depth for the afternoon. So you can see where LiDAR is on the far left, and then TKE, Stoll, Richardson, and Holsworth. And one thing to note about this comparison is you can see where Holsworth lies compared to all the others. It's basically an underestimate most of the time. And the next graphic kind of speaks a little bit more to that and unpacks the box plot a little more. But then you can look at the TKE and the Stull, and they're pretty consistent. Richardson is there too. The one thing that's slightly different about Stull and Richardson when you compare it to TKE in this particular graphic is there's a little more variance to those two compared to TKE, but they're very close. And the next graphic actually gives a little bit more information in this regard. And basically it's the same data, just put into a scatter plot for each method. And so if you just kind of look at those compared to the LiDAR, you can see the TKE and the Stull look pretty close. Richardson's pretty close, so that kind of compares to the previous graphic. But if you look at Holsworth, you can see that there's pretty consistently an underestimate there most of the time. And I think that's just the dry atmospheric assumption. And an atmosphere is never totally dry in most places. I mean, I'm in Nevada here, and even sometimes here, I mean, most of the time there's some moisture. But one thing that stands out with TKE is the cluster of points is tighter to that 45-degree line. And it is in Stull too, but there's a lot of little underestimates that basically run along the bottom of the graphic, which are, you know, Stull estimated values are near 0, whereas the LiDAR has a higher value. And that could be error with the LiDAR, but it also could be that there's quite commonly small little inversions that are missed, or you know, saying there's an inversion there that are going to get mixed out. And then there's the Richardson number, which is also doesn't have those little inversion issues, but has a lot more variance to it. And you can see those little inversion issues show up with the Holsworth too. So they're pretty consistent because Stull and Holsworth in the end are very similar. It's just you have moisture in one and not in the other. So I'm sure there's more I could say about that, but I'll wait, and I'm sure there'll be questions about that, so maybe I can address those at the end. This particular graphic shows kind of an example of what I was just talking about, where you can have an inversion near the surface that can impact your mixing height value. And it sort of gets at too, is how is the forecaster going to get the mixing height? Is it going to something he's going to do manually, looking at a sounding and pick it off, like, you know, looking at a dry adiabat or a moist adiabat or virtual potential temperature and then picking it off? Or is there going to be some kind of algorithm in place that does this and calculates the value for the forecaster, and then he takes that and reports it? So that I don't know what's going to be the case there, so that kind of makes an impact in this whole thing. But this graphic shows TKE, Richardson number, and Holsworth in blue, and Stull in red. And so you can see the TKE and the Richardson number are fairly close, you know, around 17 or 1.7 kilometers for the both of them, where that horizontal line is. But then, and I have a marker here, but then if you look at here, in the lower part of the atmosphere for the Holsworth Stull, you can see that there's an inversion in the potential temperature that basically negates a value, and what it puts it near the surface when it actually should be a lot higher, and it will probably mix out. And you can see Stull actually gets around that because you have the moisture included right in here. So that's just kind of an example. I just wanted to show that the real difference in the methods that can sometimes arise. And it doesn't happen a lot, but it happens enough to be important. So this next slide is basically a spatial representation of TKE and the components that make up TKE. And I wanted to sort of separate out buoyancy and shear, and then the combination of them, and then also effects of the terrain when you have certain flows. So this was discussed kind of at the end of the mixing height paper I put together, but it was just a way to sort of kind of relate TKE kind of to the more simplistic methods of Stull and Holsworth if you broke it down by buoyancy and shear, and just kind of see which term is operative, and basically at work for the mixing height. And so if you look at the top set here of the southeast United States, you can see that in most cases the mixing height is basically below 500 meters, so there's not much going on there. But if you go above or below, you can see in certain places that the buoyancy by Louisiana is kind of active, taking over the height of the mixed layer. And then if you go over into North Carolina, on the lee of the Appalachians, you can kind of see that there's a mix of buoyancy and shear going on. That could be, you know, some downsloping going on there, maybe some flows near the mountains on the lee side. And then over here on the right, you can just see where the mountains are there and the flow that's going on. I think I have 850 millibar flow overlaid there. And then if you go to this bottom panel, that's just a representation over Nevada, central Nevada. Kind of the two. I put two extremes on the southeast. That tends to be a lot more moisture involved, whereas Nevada tends to be, quite dry and a very different climate, arid desert versus highly moist vegetated. And you can see across Nevada, it's a real big mix. Sometimes you have the buoyancy term doing most of the work. Sometimes you have shear doing a lot of the work, and you have a combination. And that's because Nevada is just a very complex terrain environment. And if you look at the graphic on the right, you can just see the terrain profile there. And the flow is really pretty weak there. But there's just a lot going on. You've got slope aspect heating. You've got all kinds of little jets that form near the base of mountains. So it's a much more complicated situation. And that kind of speaks to you might want to use a mixing height method that can capture a lot of those different kinds of perturbations, that are going on. It's not just a static environment. So that was the point, I guess, of this graphic, was to show that there's more than just buoyancy and shear. Sometimes there's effects of the terrain. There's all kinds of little things that can basically influence the depth of the mixed layer. And so with that, I put together a table in this next slide that basically shows all the methods that I looked at and kind of the advantages and disadvantages of all of them. And the order of them really makes no difference. TK is up near the top because I kind of found that was the best method, and in terms of including all the aspects of what drives the mixed layer. I don't know how that is in application and implementing such a method and using it operationally, but I basically just looked at all the physical aspects that drove the mixed layer and compiled them. So TKE definitely stands out to me, at least, as kind of a superior method in that, because it includes all those aspects that I mentioned in the previous slide: terrain, the static stability, the wind shear. The one maybe disadvantage of that is, or maybe even two disadvantages, is it's not a straightforward calculation and requires a model to get at it, and something that's preferably a fine resolution model. I put 5 kilometers as a good example, and I used a 2 kilometer model in the study, the WRF model. Or actually, I used analysis data from RUC, but then I did a slight comparison with WRF just as another comparison. But then there's the bulk Richardson number, which is, again, another good method. It does not require a model, and it also looks at buoyancy and shear. And it's basically a component of the TKE equation. It just only looks at the shear and the buoyancy, whereas the TKE looks at all the other terms. So it's kind of like a surrogate for TKE. Some of the disadvantages is it excludes advection, and it excludes pressure perturbations. It looks at the mean state of the profile rather than the time tendency, which you can get with TKE in a model. Then there's the stall method, which again, like Richardson, it's not model dependent. You can use a sounding, and that is attractive for those kind of methods. You can just pull up a sounding and calculate the mix layer. It's quick and easy. It uses the moisture profile and considers dry, so it's good that way. And then the Holsworth method is also another quick, easy method. That's why I think it's been in place so long. But again, it doesn't look at the moisture, which even if you're in Nevada, a very dry state, you still have some moisture included there. So this kind of just puts together a summary, I thought, of all the methods and their pluses and minuses. So that might be something that might be useful for everyone who's listening. And so I'm getting kind of to the end here, but I wanted to basically put a shout out to the paper and my co-authors, Tim Brown and Gary Curcio, for their help. And it's in print now with the Journal of Operational Meteorology. And I put a direct link here, so you can basically access it online. And if anyone has any trouble getting it or wants a copy, I'm glad I got a PDF I could send around to anyone who's interested. And then just kind of as an aside, I threw this last slide in here. I thought it might be something interesting to show everyone. It basically relates to my current research, which is looking at the boundary layer, but in the tropics. And the point I wanted to make with this particular slide is that this is a calypso profile. And if you look at the top panel, you can see the orange, which is the aerosol, which I sort of mentioned earlier was the surrogate for picking off the mixed layer height. But then if you look at the bottom panel, which is a WRF model profile for the same place as Calypso, and you look at that red line, that's basically the boundary layer height from TKE. And if the aerosol in the top panel is in contact with the ground and there's no gaps in the middle, if you compare that red line along the bottom to the aerosol profile in the top, they're very closely corresponded. And so that's just another kind of shout out that TKE, even in the tropics, near the equator, is capturing the aerosol profile and the LiDAR and representing the boundary layer and the mixed layer really well. So I just thought that might be interesting because it's a completely different environment from where I did this study across the United States. So it was just more of a for fun thing that I threw in there. So I know this is a rather short presentation, but I wanted to keep it that way and make sure there was plenty of time for questions, make sure there's plenty of time for Robyn to talk. And so with that, I'll close and wait for questions and wait for Robyn to finish her stuff. Thank you.
Thanks, Matt. Once again, if you guys joined us during the presentation, my name is David Godwin, and I'm the coordinator for the Southern Fire Exchange. And that was a presentation from Matt Fearon with the Desert Research Institute. And at this point, Robyn, are you ready to go ahead?
I am.
All right, go right ahead.
Okay. Well, good morning or good afternoon, as the case may be. I'm Robyn Heffernan with the National Weather Service, and I work with two other folks, Keith Hockenberry and Larry Van Bustum, at the National Interagency Fire Center in Boise, Idaho, in managing, between the three of us, we manage the fire weather program for the National Weather Service. And we've also had presentations by Matt, thank you, for our incident meteorologists as well, sharing this information. So what I wanted to do today is just kind of tell you where the Weather Service is with making progress on our forecast, not only for mixing height, but for other smoke elements, and where we plan to go forward within the next year and beyond. So a little bit of history. In October of 2014, the NWCG Fire Environment Committee and the Smoke Committee worked together to draft a message, a letter from the NWCG Executive Board that was issued to the National Weather Service requesting that the National Weather Service, and this is a formal request, that this request has been taken in place several years prior in informal ways, but this was the first formal request from the National Wildfire Coordinating Group to the Weather Service, asking the Weather Service to begin producing smoke grids. As you know, we have gridded forecasts of many other elements, but we don't have nationally consistent smoke grids across the country. Some offices offer them as local grids, but there's no national consistency or national requirement for those grids to be offered across all the Weather Service offices. So when they say smoke grids, what essentially they mean is mixing height, transport wind, and ventilation rate are the three grids that were explicitly stated in this letter. The letter did not state a methodology such as the ones that Matt had presented here that they would like the Weather Service to use. They would just like some consistency and national offering of those elements. The study, though, the Desert Research Institute study was cited in the letter as a possible resource for the Weather Service to use in coming up with this definition for what we want to use as our methodology. So from there, the Weather Service works in milestones. Every year we, as an agency, develop milestones of kind of the high priority, high ticket items of what we'd like to accomplish for the year. So in response to the 2014 letter, in the fall of 2014, a 2015 milestone was developed by the Weather Service to formalize a team within our agency and develop a methodology as to how these smoke grids could be produced. So that team was developed in the summertime, late summer, early fall. A National Weather Service team was formed. It has representatives from all of the different regions, a variety of subject matter experts that have taken an in-depth look into this process, and a Weather Service, a union representation as well. So that team has got together. We've also been in close coordination with our partners in the Bureau of Meteorology in Australia as they are kind of going through the same process in trying to develop the best methodology to use for mixing height for their area as well. So we've taken that study, some local studies we've looked at, and talking to our partners in Australia, and we have put together a methodology as to how we would like to start producing nationally consistent grids for these smoke elements, mixing height, transport winds, and ventilation rate. The current process that we're going to use for this is right now we're evaluating that methodology. We're actually having some experimental grids being produced at some of the local offices so we can take a look at them and see what they look like and any weaknesses in the methodology process we want to rectify. From there, the 2016 milestone for the Weather Service is to, by the end of 2016, start producing these smoke grids experimentally. So where we need to go with the process from here is once we have gone through the process of actually seeing these experimental grids through this small team and mitigating any of the weaknesses there, we are going to then negotiate with the Weather Service regions and the Weather Service Employees Organization for agreement on how to produce these nationally from all of the regions. Once we get that in place, then that's when we will actually work with our modeling group in having them start being produced. So we're a couple stages away. We certainly are well into the process, but we're a couple stages away from actually having those grids produced. Like I said, it is a 2016 milestone, so by the end of 2016, if all goes well, we should have some of these grids being produced nationally across the board in an experimental mode. The biggest challenge we have as an agency in producing forecasts of mixing height and transport wind and ventilation rate, they kind of all go hand in hand because transport wind and ventilation rate all depend on mixing height, is the fact that we don't really have a great measurement of mixing height. And so the best way we've been able to measure it in the past is by using soundings. And when you use a sounding to verify a forecast of mixing height, you are inherently biasing that verification because you're using the same methodology to verify that you used to forecast. So any of the biases that were there in the forecast will still be there in the verification. And so it's not a great verification method. What Matt has done here is completely independent. It's how we need to verify mixing height. But this can only be done right now on a study type basis, and we don't have continual data coming in. So in order to make sure that our process continues to stay on a positive track and continue to improve, we are working with the observation groups within the Weather Service and possibly trying to use thermometer data from our ASOS stations, which are our weather stations across the country, and see if we can use that data to determine a mixing height level in order to assess our mixing height forecast. And that will help us improve not only whatever we decide on this first round of our methodology for experimental grids in 2016. I mean, it's not a one-time deal. We will continue to evaluate those grids and improve on them as we can as we go forward in time. But when those grids are offered experimentally, they will be offered up to the fire community, and we would welcome your input into how you feel that those grids are producing a mixing height forecast for you and your fire management purposes. We also would like to express that we do intend on running any new forecasts with new methodologies side by side with any existing forecasts that the local offices are currently doing in this realm. So folks and fire managers that are used to a particular method in your region of the country, you would be able to see those forecasts run in tandem with the new methodology at the same time, so you can see what the differences are between the two mixing heights. And it gives you a period of time to account for those changes, get comfortable with them, and be able to work with your local office on any issues that may arise. So that's all I have, and when we're ready, I'll take questions.
Yes, I think we can go ahead and take questions. We have plenty of time left in our session.
Okay.
It looks like we have a question from Lita Kobzar. Can you see that there?
Yes. So the question has to do with gaining feedback from the fire community. Is there a mechanism in place for this? So anytime the Weather Service produces an experimental product, we will have a survey that will be set up for that experimental product for you to submit your feedback to the Weather Service on that. As always, you can talk informally with your local office and certainly communicate with them and keep in contact with them as well. But the formal process will be through the survey, which is similar to any experimental product that the Weather Service produces.
It looks like we also had a question come in from Joe Royce about would this new process eliminate the variation when we cross county boundaries going from one forecast area to the next, I guess?
That is one of the goals of doing a nationally consistent methodology would be that we would minimize the variation across boundaries. It's hard to say that we would ever eliminate it altogether. For a variety of reasons, but definitely that is a big goal of our process here, is to minimize those boundary issues as much as we possibly can.
And then it looks like Robyn Joe Royce had another follow-up. He says, not clear to him which is the methodology the National Weather Service will be using.
That's because I didn't say it. So the reason I didn't specifically say it is because we are still evaluating our process. What I can tell you with regard to Matt's study, there's different elements of the methodology that we're putting in place. A lot of it's very internal to the Weather Service, is to not just how mixing height would be calculated, but how the actual grids would be calculated from model data, how our forecasters would edit it, and all that type of stuff. So that's all encompassing when I say methodology. With regard to the calculation method for mixing height per Matt's study, right now we are leaning towards the Stoll method. Couple reasons for that is, as you saw per his study, it verified very closely, as well as the TKE. It didn't do quite as good, but it was very close second to verification to the TKE, and that it can be calculated off the sounding, which is pretty critical for our forecasters in this environment right now where we don't have those independent observations. We go down the road to the salometer data, hopefully being able to provide that for us. I think it kind of opens the door a little bit more to being able to go down the TKE route. But nothing's been decided at this point in time, but that's where the team is headed. So Margaret had a question about the hurdle to implement TKE nationally. I think I just touched on that, and if I didn't, Margaret, please comment again and let me know if I didn't answer that. But it's the observations that we're missing, and the fact that since TKE cannot be manually calculated, it's kind of a black box for our forecasters. So it's really challenging for them to be able to look at a model output of TKE and be able to add any sort of forecaster value to it. An example would be if a forecaster was looking at a particular model output and they knew that that model was bringing in a system too quickly. So they would edit their grids accordingly. They wouldn't really know how to edit mixing height because the TKE method is kind of a black box. So I think to learn a little bit more about that method, it'll open the doors somewhat if we actually have those surface observations of the atmosphere and the mixing height levels that would tell us real-time data on that, and I think that would be helpful.
You see there's a question that came in from Matthew Fearon about the timeliness of this data that's going into these grid forecasts. Is it going to be an hourly product?
Let me get back to you on that. While we're going through some of the other questions, I have to look up something to be able to answer that for sure. I believe the requirement is 3 hourly that we received from our customers, but I'll pull up a file here as we're going through some of the other questions and be able to get that answer for you for sure.
Okay, thanks. You see Cave had a question that came in on timeline for the implementation of this. Any idea there?
So the timeline for implementation is 2016. By the end, I can't tell you exactly when. It is a fourth quarter milestone, meaning that we have to do it no later than the fourth quarter, obviously. But because of the timeliness it's going to take us to negotiate agreement across all of our regions and whatnot, we gave ourselves the entire year to accomplish this task. But it is a 2016 goal, meaning by the end of the fiscal year, 2016, that we would have these grids being produced experimentally. Could be sooner.
And those grids would be available through the local National Weather Service office websites?
They would be both locally and national. So they'd be on both of the sites. And like I said, what our goal is when we go forward to actually implementing these experimental grids, that any office that currently does some local grids of mixing height, that they can continue to run those local grids. These other grids are being produced as well, so that customers can see what the difference are. And it's kind of analogous, I guess, to say with some of the fuel model changes that we're currently going through, where we're going to see some of the data, dual data, so that we can see comparisons. Same idea that we want to run with here, so that folks have a transition period to be comfortable with the new process. Okay, so I have the answer to the other question. It is the requirement for these grids is going to be 3 hourly out to 72 hours is when they will be produced. So every 3 hours out to 72 hours in duration.
It looks like, and just a comment directly on that from Gary, you can see there.
Okay, point taken. I think we're starting with 3 hourly, as that was kind of a general requirement from the wildland fire community. But once we start producing these grids, like I said, this isn't a one-stop deal. We're going to continue a process of evolving and improving them. If they verify very well on a 3 hourly time frame, it's possible we'd be able to break them into 1 hour chunks and see how that does as well.
So at this point, we've run up to the end of our time, I think, for the webinar. But I'd definitely like to thank Matthew and Robyn for joining us today and for your great presentations. And thanks everybody who participated with your questions and attending this. And again, thanks also for all the partner organizations that came together to help make this collaborative webinar possible. So appreciate it, everyone. Hope you guys have a good afternoon.
Thanks, Robyn.
Thanks, Matt. Thanks, Robyn. it.